Hi everyone, this is Saptaswa Ghosh from Indian Institute of Technology, Gandhinagar. So I'll be presenting a poster in Strings 2025, and the title of my poster is Bootstrapping Classical Two-Body Problem in Theories Beyond GR using worldline quantum field theory. So I will discuss basically some aspects of computing the gravitational observables in scalar tensor theory and the dynamical Chern-Simons theory that are basically beyond GR theories using the techniques of worldline quantum field theory. So first I will discuss what are the basically observables in classical two-body problem uh, in some scattering event, and then I will discuss basically how the worldline quantum field theory plays a role, very important role in computing the observables directly rather than going through some direct amplitude based approaches. And it basically actually connected to some uh, worldline representation of the gravitational at rest scalar propagator. That is basically we are scattering some scalar field. They are basically the avatar of the black holes, and they have some worldline type representation, and that is the main point of the worldline quantum field theory. And in worldline quantum field theory, the observables are basically the one point function in WQFT, and they are related as this. And basically, in the classical limit, in principle, the partition function in the worldline quantum field theory can be exponentiated as this, where chi is the iconal phase. And if one computes the iconal phase, then from iconal phase also one can compute what are the observables by taking suitable Poisson bracket. They are basically the cases for the spinless scattering. And if we have some spin, then the worldline action actually have some spinning degrees of freedom also. And in worldline quantum field theory, what we have is that we have the path integral over the bulk fields as well as the worldline degrees of freedom, that is basically the trajectory. But if we have spin, then the spin is also some worldline parameter, and we have and people introduce some Grassmann number, Grassmann field psi, uh, with along with the uh, x, that is basically the degrees of freedom for the trajectory, dynamics in the trajectory. And for spinning case, we have the path integral over the bulk fields as well as the path integral over the x mu and also the size. And this action basically has some n equals to 2 supersymmetric invariance, and from that we will discuss how basically this supersymmetric invariance implies that we can choose some supplementary condition, because in principle this equation, that is classical equation of motion for spinning particles, has some redundancy. So we take these two theories, that is scalar tensor theory and the DCS theory, where one has some only scalar field as an extension of GR, and another has some scalar field with some higher curvature term. So, so we computed basically the uh, observables in scalar tensor theory and the iconal phase in DCS theory. So there are some, I will discuss also some of the computational technologies which have some non-trivial IBP reduction procedure and some method of differential equation, how to solve the integrals there. And I will discuss also, we are in a classical limit, but also although we are in a classical limit, we will face some loop integrals with some delta function constants. And also I will discuss some of the results, the master integral results, and also the what are the expression of the iconal phase in DCS gravity, and also discuss some aspects of the computation of the waveform, time domain waveform in scalar tensor theory, where the bulk scalar field is massive. Then some non-trivial things are happening, because from the frequency domain to time domain, that is basically a Fourier transform, but the Fourier transform here for the case of massive scalar fields is not the kind of a one-dimensional Fourier transform. So we take the some method, stationary phase approximation, and we got some results out of it, some sensible results. So that's it, and thank you.